Welcome back to ECE 441A, 541A. Announcements. Right after class, I'm not available for office hours. I have to disappear and go somewhere else quickly on campus. But lab number 1 is due on Monday. Homework 3 is due a week from Monday on the 10th. And exam number 2 is a few Fridays from now on the 21st of October. And if you haven't already, you might want to watch lecture 3.1. We only have a full screen of goals today, but maybe there are not as many as the text indicates. I want to recap by going through the scalar case. We're talking about the state transition matrix today and what that looks like. Remember, that was e to the AT. We'll remind ourselves what that looked like in the scalar case. Today we'll quickly walk through the vector case when we have a two-dimensional state vector. And then we will look at the state transition matrix, which is e to the AT. We'll maybe define that to be a capital phi of t. And just because it's Friday and it's been a while, let's just make that our third cheer. So phi is equal to e to the AT, and hopefully you'll remember that. I think this is our third cheer. We had cheer 1, which was, well, I saw a t-shirt on the way over here, and it said, if you're happy and you know it, clap your hands, and I think it was a dinosaur, so I don't know that the dinosaur could actually clap their hands. So that got me thinking, if you're happy and you know it, let's do a cheer. And so I said, let's introduce cheer number 3 this morning. So that's phi of t is equal to e to the AT. We'll look at two different ways of computing that matrix exponential, e to the AT. We'll do it with paper and pencil, and we can also show it with a calculator. And I'm already preloaded with my calculator, so we're ready to go, hopefully, to start typing in some of those equations on the calculator. And then we'll do this as we go, but I want you to be clear on the poles of your transfer function being the same as the eigenvalues of the system matrix. So if you know one or the other, you know a lot about the characteristic behavior of your system, how it naturally wants to shake or how it wants to behave. As a recap, we can find our system or how it shakes by looking at this solution to this differential equation. We have the scalar case, little a, little b, and little c are all scalars. They're 1-by-1 matrices. And that makes this process easier to work through. We don't have to worry about inverting matrices. We simply are dividing by polynomials. But we're starting with this differential equation. It's first order. We can Laplace transform that differential equation, and we end up with s times x of s minus the initial condition. When we Laplace transform a derivative, we have s, obviously in the frequency domain, but to keep track of what can happen dynamically or in the system response, we need to introduce or keep track of that initial condition, and that's minus x at time 0 minus. Then the Laplace transform of the right-hand side is easy because we're just defining basically those Laplace transform quantities. The Laplace transform of little x of t is capital X of s. The Laplace transform of little u of t is capital U of s. And those scalars, a and b, because they are constant, they slide out and they don't really impact the Laplace transform. We can now solve for capital X of s by factoring the terms or the coefficients that multiply or scale capital X of s and put those on one side. So we're taking the little a to the left, and we're taking the initial condition to the right. Now we divide by that factor s minus a, which when we get into the vector case, this factor is going to be consisting of matrix elements. And we can't just divide by a matrix. We have to invert it, and we have to do that in the proper way. If we say, oh, we're inverting a matrix, we have to know which side we're putting that matrix inverse on, because matrices do not commute. AB is not necessarily BA in terms of matrices. But here, since we're dealing with scalars, it really doesn't matter. And now we have an expression for capital X of S, and it's made up of two pieces. One piece is due to the initial condition, x of 0, and the other piece is due to the forcing function, or the input, and that in the frequency domain we've called capital U of S. And here is our recall from an earlier class. For example, we should remember that in Laplace transforms, if we have these Laplace transform pairs, in the table you should see e to the at paired up with this inverse Laplace transform, or the Laplace transform of e to the at is 1 over s minus a. That you should have in memory, and maybe you should have that in memory until even after retirement. You should still be remembering 1 over s minus a has an inverse Laplace transform of e to the at. Knowing that fact allows us to take this frequency domain expression for capital X of S into the time domain, and remembering that when we have this product of frequency domain quantities, that corresponds to convolution, and that's why we end up with that convolution integral as the piece of our total solution for x of t coming to us from the forcing function, or u of t. The input then drives the system response, or the system's behavior, x of t, through that convolution integral. And that convolution integral, inside it is this piece of the state transition matrix. So you're convolving this e to the at, and what does e to the at look like if a is stable? If a is stable, what is little a in terms of its sign? Is it positive or is it negative? Little a. It's negative. It has to be on the real line. It's negative. It's stable. Now we're looking at e to the minus 6t, e to the minus 0.1t. Those are stable, but you can visualize what that looks like. That's this exponential. You're now in the convolution integral convolving that exponential shape with whatever u is. If u is a constant, then you're convolving that exponential with a constant. If u was an exponential, you would have these two exponentials being convolved. If u was a sinusoid, now you have this convolution of the exponential with the sinusoid. Luckily, we have computers that do that. And they're sitting in the front row, right? Okay, they're sitting in all seats of the entire classroom. I was just picking out a sample. So now let's move on to the vector case. Now you can stay busy by taking notes, and let's now look at the vector case where we now have x prime of t equaling a, but a now is this matrix A, and you can read a lot into capital A. What are its dimensions? Or what's its shape? What's the shape of A? It's square. And depending on the dimension of x, how many state variables you have, in the lab, how big is your state vector x? How many states do you have in lab number 1? 2. You have position and velocity. That just allows you to describe your system's behavior. Then we have plus b u of t. B will be the same height or the same number of rows as A. It's also the same number of rows as your state vector x. How wide B is depends on how many inputs you have u of t. Then we also can have our output equation. Y of t is c x of t. We're assuming that these matrices A, B, and C are constant, and that allows you to text LTI, right? This is now a linear time invariant system. Constant implies the time invariant. The linear is on the right-hand side, what kind of combinations do you have with your x's and u's? They're just linear combinations of those x's and u's. So this is a linear, and the constant piece gives us time invariant. So is the input 0 in this case? Was one of the questions. Is the input 0? The question really was, what happened to D? I just was assuming it was 0, but it can be there. But that doesn't mean the input is 0. That just means that the connection between the input and the output, there may not be a direct connection. Meaning the input gets somehow filtered or adjusted by going through the system. It has to go through x prime equal ax plus bu before you see it in the output y. So there's some dynamic behavior between the input and the output. And a lot of times I will get lazy, or I will get, well, most of our systems are strictly proper, so we don't have a capital D matrix. But in general, it will be there, but I probably in today's class will leave it off. Just it makes it quicker for me to write down. But it is there, but even if it's there, well, even if it's not there, doesn't mean that the input is 0. That just means that you don't have an input connected directly to the output. You can't wiggle the input and instantly see it at the output. But with this structure in the vector case, we can still do the same kind of steps that we did in the scalar case. We can still Laplace transform this. What happens if we Laplace transform a vector of derivatives? That's what x prime is. It's just s times all of those components. And we can write that as x, capital X of s. That looks no different. We just have to remember that x is tall and thin. It's now maybe Nevada tall, n, little n tall, minus x of 0 minus, and that vector has to be the same height. That's our initial condition. So if we have a state vector that's position, velocity, current, voltage, those all get stacked up, and those are our x. x1, x2, x3, and x4. That's now equal to a capital X of s plus b u of s. And at the same time, we can Laplace transform the output equation. Now you forced me to carry that D around, but we'll maybe drop it, maybe we won't, but we'll see. Okay? It just makes it have some more terms that I wasn't really wanting to keep track of today. I'm getting lazy. It's a Friday. All I can do is cheer, right? So we may drop that in a minute, but you see what we've done, I hope, so far. We've simply Laplace transformed this system dynamic equation, x prime, and the output equation, y. Question? So the question was, where are these initial conditions? X is our dynamic behavior. That's capturing the dynamics of our system, and that's where we have our initial condition term. The output, you do have initial conditions on the output, but those are coming through the state vector x. Y is a linear combination of x and u, so if you have initial conditions on the output, those are really being there because of your initial conditions on the x. So we don't have to specify the y, and the output equation is simply a linear equation. There are no dynamics in the output equation, and so we don't get any s's floating around, and we don't see any initial conditions coming in our output equation when we Laplace transform. But I want to now combine my terms that have capital X of S with them. And this little s is a scalar, and that's sort of making things a little more difficult, but I can make that easier by introducing an identity matrix. And how big is that identity matrix? It's the same size as A. So if A was Nevada by Nevada, N by N, then I is N by N, and I only has ones on the diagonal. All the other elements are zeros. But that now allows us to have Nevada S's. We had it before, but now we want to combine that with the A matrix, so we can pull the A matrix term over to the other side, and we now have Si minus A, capital X of S. I'm going to put the initial condition on the right-hand side. To give me that. And I can now solve for capital X of S as I did in the scalar case, but now I need to invert a matrix. That Si minus A, maybe you know all the entries in your system matrix A, but S is a variable. You now have to do a symbolic matrix inverse, which if it's 10 by 10, that's okay on the exam probably. You now have to carry those 100 elements in that inverse around. You have to do a 10 by 10 determinant, etc., but it's doable. The exam is 50 minutes. But I'm now inverting on the left. I have to keep track of where I'm putting that matrix. I'm now inverting. I'm hitting all three of those terms with Si minus A, that quantity inverted. Meaning I now have an identity times capital X of S, but I have Si minus A inverse times the initial condition plus Si minus A inverse B U of S. And you can actually guess or speculate what the structure of this Si minus A as a matrix inverted is going to look like. We know, I'll do the hard part. Capital X of S, and if I go into the time domain, is little x of t. That was the hardest part. No. Teasing. But I want to now find the solution, little x of t in the time domain. Si minus A inverse, what was that in the scalar case? That was 1 over S minus A, where A was scalar. What did that end up being in the time domain? That was EAT, wasn't it? E to the AT. Well, that's exactly what it is in the matrix case. It's just that now we have this matrix in the exponent. We have E to the AT times x of 0 minus. How big is E to the AT? It's a matrix. How big was A? Nevada by Nevada, so E to the AT is the same. It's square and it's N by N. And we'll get more comfortable with E to the AT in a little bit. But we now can have two pieces, Si minus A inverse, that's one frequency domain term, and capital U of S, that's another. We need to convolve those. Now we have this convolution integral with matrices, which is e to the A t minus tau b u of tau d tau, where this piece, e to the at, is our state transition matrix. That, when combined with the initial condition, gives us our initial condition response. And the second piece, which is this convolution integral, gives us the response due to the input, and that we could call our forced response. Which, if you have zero initial conditions, the only thing that's going to influence your response is the input piece. If you have zero input, that second term goes away and all you have is this initial condition response. And you now have to figure out, what does e to the at look like as a matrix, because I want to now combine those matrix elements in e to the at by my initial conditions in the x of 0 minus. And how those combine then influence the system response, little x of t. But that's now my complete response. It's made up of two pieces, an initial condition piece and a forced response piece. And one of the homework problems, I believe, assumes zero input, which means you simply have to worry about this left term on the right-hand side. You need to be able to do the e to the at and scale that by the initial condition. Now, what if we go back? What if we now say, I want to go back to a transfer function? I now can play or work with these frequency domain expressions. Meaning I know that y of s is c times x of s, and with the earlier question, that's du of s. And now if I want to find y of s, I can find it because I have my x of s expression. That's c times what x of s was, and that's right here. That's c times those two terms. So I have c times si minus a inverse x of 0 minus plus c times si minus a inverse b u of s, and I still have to keep track of this plus d u of s. Now, if I want the transfer function, what have we been doing when we have the transfer function? This now, if I inverse Laplace transform this, this would give me the complete solution for my output. This would give me little y of t. But if I'm after the transfer function, I don't care about this response so much as I want the system dynamics or the behavior of the system in the frequency domain. Meaning I don't care about the transient behavior, I just want the dynamic behavior. Or I can set my initial conditions to 0. And if I do that, what happens to those three terms on the right? Anything if I set my initial condition to 0? If if my initial condition vector x of 0 is 0, I'm annihilating that entire first term, aren't I? So that I now have y of s is equal to c si minus a inverse b plus d. I'm now going to factor out my u of s from those last two terms. Question? So the dynamic behavior is how the system shakes or how the system moves. If you now wanted to find if you had a circuit and somebody said, oh, what's the dynamic behavior of this? Then the dynamic behavior of that can be described by the transfer function. If they say, I want the complete solution, then you have to worry about how to incorporate those initial conditions into your response. But if they just want the dynamic behavior, they are now after this g of s, which is our transfer function. And this relationship right here, that looks like a not equal to, so maybe I won't do that. But this g of s was our first cheer, that expression. C times Si minus A inverse B plus D. If you know the A, B, C, and D, you can find the transfer function in the frequency domain. And what we are seeing when we're doing these solutions, when we're looking at time domain, when we're looking at frequency domain, we're actually seeing this Si minus A inverse matrix appearing a lot. And it provides us with information on how the system transitions between different points in the state or in the system. And that's why it's called the state transition matrix. Meaning, this y of s equation had c si minus a inverse x of 0 minus plus c si minus a inverse b u of s, and if we had the direct feed-through term, there was this plus d u of s. But you can see that in this, most of this, if the output is not directly connected to the input, this Si minus A inverse is appearing throughout. And that is then this Si minus A inverse, and we want to know, or that's defined to be what we're calling the state transition matrix, which is e to the at. And in order for us to remember that, I've just decided today, since I saw Barney, I don't know, a dinosaur earlier on a t-shirt, wherever that came from, this is now our cheer number 3. So if I give you a phi of t, what are you going to echo back? E to the at. You're hungry, right? Eat. But A and T are shifted up on your typewriter. But you now have E to the at. But if you sort of read creatively, that's now eat. And eat requires energy or a transition to happen. So phi of t is equal to e to the at. We want to be comfortable with computing e to the at, or finding that, or knowing what that looks like. And sometimes to understand what something is, we identify what it is not. So let me show you, or explain, or just tell you that e to the at is not the following. If I give you a matrix A, which let's say is -3, -2, 1, 0. Although it may be wanting to be done this way, e to the at is not each individual element exponentiated. It's not e to the -3t, e to the 1t, e to the -2t, e to the 0t. That is not what e to the at is. E to the at is a more interesting matrix than that. So we can't just raise each element or exponentiate each element in order to find or to be able to cheer or perform cheer number 3. We have to do a little bit more work. And maybe if, did you see this with your pickaxe in differential equations where e to the at, did you talk about that as a matrix? No. Well, it's defined as a sum of terms. I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, and that pattern just keeps repeating. That's a series, isn't it? And now we would have to, but we don't want to compute it that way. If you had A as a 100 or a 10 by 10 matrix, we may not be wanting to cube it and raise it to the 4th power, etc. This converges quite quickly, and you can do this with different algorithms that do not do this term summation. We don't want to compute each of those terms and add them up. If you do this with paper and pencil, here is what I would suggest. This is one of the reasons that you like Laplace transforms. You sort of play with it in the frequency domain, and boom, you inverse Laplace transform at the end, and your answer pops out. Now, we know by definition that e to the at was equal to the inverse Laplace transform of Si minus A inverse. And a lot of times we just call that state transition matrix capital Phi of t. I sort of always like writing e to the at unless I'm really hungry, and then I have to go take a break and get a snack and come back. But e to the at is now this inverse Laplace transform of Si minus A inverse as a matrix. If capital Phi of t is that, then capital Phi of S would be the Laplace transform of capital Phi of t, which is just this piece right here, Si minus A inverse. Let's look at computing that. Suppose that we had a system that's second order, and we want to know how is this system, or can we find the response of this system to initial conditions or a forcing term or both. Meaning, first let's find the state transition matrix. Phi of t is e to the at, which is this inverse Laplace transform of SI minus A inverse. That's the inverse Laplace transform. Now we put all of that into a matrix. What's SI? S times an identity matrix. How big is the identity matrix? It's 2 by 2, so I'm going to combine SI minus A into one matrix. I now have S in the 1, 1 entry, and now I have a minus 3, so that's S plus 3 in the 1, 1 entry. I have a 0 in my SI in the 1, 2 entry, and I'm subtracting 1. Do we see where these are coming from? Then in the 2, 1 entry, what do I have? I just have minus 2. And then in the bottom, in the 2, 2 entry, I have S minus the A, which was nothing. And I now need to invert that matrix symbolically before I start inverse Laplace transforming. How many have a TI-89 or a TI titanium calculator? Well, you can do that with your calculator. You could now say something like, S is kind of buried, but X is there, so let's just use X instead of S, and you know what I'm doing, I hope. But you might say X plus 3, comma, minus 1, semicolon, 2, comma, whoops, X. And now you might raise that to the minus 1 power, and voila, you'll get this 2 by 2 symbolic matrix inverted. Or, if you have the Inspire, you could do the same thing. You could go over, and here S is a little easier to find. It's right there, so I'll do S. Then I'll say times. Did I get a times? I'm going to have to start cheering to this calculator to get it to move. Then I'm going to do a square bracket. And what was this? This was S times the identity. And the identity was 2 by 2. I need a 1, comma 0, semicolon, 0, comma 1. And now I have my SI matrix. I can now go back and get that and not have to retype it, minus my A matrix, which is, again, control bracket. This was minus 3, comma, what was it? 1, semicolon, minus 2, 0. So there's SI minus A. Hopefully that looks like what we had. I'm going to go back and get that. So up arrow and then enter it again. And now I'm going to say, why don't I just invert that? So I'll raise it there to the minus 1. Drum roll, please, or cheer, or whatever you want to do. And there's now our matrix inverse. I don't care about a warning. I'm cheering. It's okay. We're still okay. We have SI minus A inverse. And eventually, we want to take that into the time domain. And so we might want to, which one is it? Is it, now I've forgotten what my function is. I think that's what I thought. It's expand. And now I just go up here. There's my partial fraction expansion, ready to be inverse Laplace transformed, and in 4 lines, I'm now ready to go. Okay? TI Inspire. It's inspiring. I actually, no, I don't get a commission, but anyway. So let's do it by hand. Yes, this is, we're all cheered up. We're ready to go. Now this is the inverse Laplace transform of this guy. So if we now invert this matrix symbolically. What's the matrix inverse? 1 over the determinant times this matrix of cofactors transposed. No big deal. So what's the determinant of this matrix? Diagonals multiplied together minus the off diagonals multiplied together. So I have S times S plus 3 minus, boy, this thing is really, times minus 1 times 2. That's my determinant. Is that okay? Thank you. That was a minus 1. So I'll have S squared plus 3S plus 2. And now I need my 1, 1 entry. That's the determinant of what's left when I eliminate the first row and the first column, which is, now I want this guy, it's cofactor, and that's simply S. Then if I want the cofactor for the 1, 2 entry, I look at the determinant of that, and all of these are going to be multiplied by minus 1 to the 1 plus 1 power. It's a 2 by 2, and it's first row, first column. And I'm going to actually be, let me go ahead and do the transpose later. So I'm going to just say, what's the cofactor of the 1, 2 entry? So it's what's left, and I take the determinant of what's left. What's left after I've eliminated the highlighted blue? 2. And I scale that by first row, second column. What? You guys are giving me a hard time, and I'm just trying to show you what's going on here. So I wouldn't have to do this, but I think it's important. You need to learn this. So let's go with this guy. The 2, 1 entry. Enjoy it. This is fun. Now we're getting rid of that one and that one. What's the determinant of what's left? Minus 1, and we raise it to the minus 1 to what power? Second row, first column. So that's going to change the sign of that one. And finally, I need to yeah, you guys laugh. This is more challenging than you think. So now, because this keyboard's not keeping up with me, I'm just too fast this morning. This is now that eliminated, and take the determinant of what's left, which is S plus 3, raised to the minus 1 to the 2 plus 2 power, and I'm going to transpose all of that. Meaning, I now have this is equal to the inverse Laplace transform of S squared plus 3S plus 2 and transposing that matrix, I have S plus 3. The diagonals don't move when I transpose. The minus 1 in the 2, 1 entry is scaled by a minus 1. It pops up to the first row, so I now have a 1 there. And what happens to the 2? It's now minus 2, and I bring that down in the 2, 1 entry. Meaning, I now have my matrix that I can inverse Laplace transform. I have S over S squared plus 3S plus 2. I have 1 over S squared plus 3S plus 2. I have minus 2 over S squared plus 3S plus 2. And I have S plus 3 over S squared plus 3s plus 2. I have 4 elements in that matrix, and I now need to inverse Laplace transform each of those. Question? I put the transpose sign there, and then I hopefully did the transpose, and now I have that result. And now this is why you took 320. You needed to learn how to inverse Laplace transform. These are all similarly Laplace transformed. You have to factor the denominator, which has factors of, just do the quadratic formula if you don't see it, but it's s plus 1 times s plus 2, isn't it? So we have eigenvalues or roots of -1 and -2, and if we did that factoring, which lo and behold, something actually did it for us, there's the factored form. This third row should be what we just computed by hand. The s over and the 1, 1, and the 2, 1, we have -2 over s squared plus 3s. Hopefully that's what we had. And we can now write down, we have -1 over s plus 1. We do a partial fraction on each of these terms. There's the 1, 1 term. The 1, 2 term, 1 over s plus 1, -1 over s plus 2. And you can instantly inverse Laplace transform those, right? That's just 2 immediate expressions. -2 over s plus 1 plus 2 over s plus 2, 2 over s plus 1, and -1 over s plus 2. Which now allows us to say that our e to the at is now minus e to the minus t plus 2 e to the minus 2t. Right? And there is, what were the eigenvalues of that A matrix? They were actually -1 and -2, and look how they're influencing our state transition matrix. They give us terms, e to the -1t, e to the -2t term, and those will be linearly combined in this e to the at term, or in this e to the at matrix, or our state transition matrix. We have e to the -t minus e to the -2t, minus 2 e to the minus t plus 2 e to the minus 2t, and finally 2 e to the minus t minus e to the minus 2t. That's e to the at, which is not just exponentiating each of the entries in our A matrix. Do you see an e to the minus 3t anywhere? No. Do you see an e to the 0t anywhere? No. And now what do you see? You see linear combinations of these eigenvalues in your exponent in each of these terms. E to the minus t and e to the minus 2t. What if you were interested in an initial condition response? Because now we know, wow, where am I? Here's our complete solution. X of t is e to the at x of 0. If we do not have an input, we now have our total solution. We simply find what the initial condition is and multiply that state transition matrix on the right by that initial condition vector. And that gives us a linear combination of e to the minus t's and e to the minus 2t's, making up x sub 1 of t and x sub 2 of t. If the initial condition vector happened to be, let's say, x1 of 0 and x sub 2 of 0, suppose that that was 4 and 7. Now you can post-multiply that 4, 7 by this e to the at and obtain x sub 1 of t and x sub 2 of t. I may do that offline, but we've done a lot today. I think you need to give yourself a cheer. Phi of t, e to the at. I'll see you on Monday.